In program-driven I/O, the processor takes the complete control of the I/O operation by executing a program. In interrupt-driven I/O, we reduce this overhead to the processor since the I/O device takes some initiative. Whenever the I/O device needs some attention, it generates a hardware signal called interrupt to the processor. Till then, the processor can continue with its work. Here in this example for I/O read request in program-driven I/O, after issuing the read request, the processor should keep on polling the device at regular intervals. So, if the device is not ready, the processor is unnecessarily busy waiting without doing any useful computations. Also, situation may arise in which the device is ready but the CPU is not known about it at that time because checking the status is done at regular intervals based on a program. But if we are using interrupt-driven I/O, after issuing the read command, the processor can continue with other useful computations. By this time, the I/O module or the I/O interface will collect the data from the I/O device, and when the data to be transferred is ready, it can generate an interrupt signal for the processor. Hence, the processor can now temporarily suspend its computations, read data from the I/O module and write it to the memory. Similarly, any kind of I/O request can be done. So here there is no busy waiting and no wastage of processor cycles. As we know, interrupt is actually a signal used to inform the processor about an exception to be handled and is used for many other situations. Here we are using interrupt to handle the I/O operations. So here we need a dedicated control line called interrupt request line, and the action to be taken by the processor when an interrupt is generated by an I/O device, or the routine to be executed by the processor in response to an interrupt signal from an I/O device is called the interrupt service routine for it. So, for an interrupt from an I/O device, there will be a corresponding interrupt service routine to be executed by the processor. Actually, things are more complex. There will be many I/O devices and different interrupt service routines corresponding to them. So to understand the normal flow, consider there is one I/O device and an interrupt service routine corresponding to the I/O device. And the address of that interrupt service routine is known to the processor or is hardwired into the processor. Suppose the processor had been computing something. In the midst there was an I/O request. Let it be an I/O read request. Now the processor can issue a read request command specifying the address of the I/O device, and then the processor can continue with its computations. By this time, the I/O module can collect data from the I/O device, and when the data to be transferred is ready, it can generate an interrupt signal to the processor. When the interrupt is received by the processor, suppose the processor was executing instruction I and the next instruction to be executed is I plus 1. Now the processor will complete the execution of instruction I and is ready to move to the interrupt service routine corresponding to the device. Before moving, it will save the address in the program counter, which is the address of the next instruction to be executed will be saved onto some temporary storage such as stack or some dedicated register. Also, since we are now shifting to an entirely different user, the current state of the processor will be saved. Everything, all the required information which is required upon returning back will be saved. Then the processor will load the address of the interrupt service routine to the program counter. Hence, next the processor will execute the program counter address or the address of the interrupt service routine. In other words, the processor will jump to the interrupt service routine. Also, proper steps will be taken to acknowledge the device about its interrupt is being processed. Then the interrupt service routine is executed, and by the time the routine is completed, proper steps will be taken to load the program counter with the saved address. This will return the control of processor execution back to the correct point to be resumed. This is how a basic interrupt-driven I/O works. Here also there is overhead due to context switching and a complex circuit. Anyway, compared to program-driven I/O, it saves a lot of CPU cycle and avoids busy waiting.